Hello everyone. I'm Dr. R. Pitchailakshmi, lecturer, PG and Research Department of Mathematics at Seethalakshmi Ramaswami College, Tiruchirappalli. In this session, we are going to learn about groups and its applications. Algebra. Mathematics as a subject can be broadly divided into three significant branches: arithmetic, algebra, geometry. Algebra is considered to be one of the oldest components in the history of mathematics. Algebra deals with the study of symbols, exponentials, known and unknown variables, and equations. Types of algebra. Algebra is divided into two types: classical algebra, abstract or modern algebra. Classical algebra has been developed over the period of 4,000 years, while abstract algebra has only appeared in the last 200 years. Abstract algebra in the 19th century, algebra was no longer restricted to ordinary number systems. Algebra expands to study of algebraic structures such as group, rings, fields, modules, vector spaces. Basic concepts of algebra. Operation. An operation takes the element of the set, combine them in some way, and produce another element. An operation combines a member of a set. Binary operation. The binary operation of the set is the operation involving two elements of the set to produce another element of the same set. Well defined. One thing about operator, they must be well defined. If I give two numbers and a well-defined operation, you should be able to tell me exactly what the result is. Example, there is only one answer to 5 plus 3. That is because the operator is well-defined. History of the group. The earliest study of group as such probably go back to the works of Lagrange in the late 18th century. The concept of groups arose from the study of polynomial equation, starting with Galileo's in 1830, who introduced the term groups. Introduction of a group. Definition. A group is a set G combined with a binary operation star such that the group contains identity, the group contains inverse, the operation is associative, the operation is closed ended operation. G1. The group contains identity. There exists an E in set G such that A star equal to A and E star A equal to A for all elements A in G. If you use the operation on any element and the identity, we will get that element back. For the integer and the addition, the identity is 0 because 5 plus 0 equal to 5 and 0 plus 5 equal to 5. In other words, it leaves other element unchanged when combined with them. There is only one identity element for every group. The symbol for the identity element is E, G2. The group contains inverse. For all A in G, there exists B in G such that A star B equal to E and B star A equal to E. If we have element of group, there is another element of group such that when you use the operator on both of them, we get E, the identity element. For integer and the addition, the inverse of 5 is minus 5 because 5 plus minus 5 equal to 0. Inverse are unique. Make a note that while there exists only one identity for every single element in the group, each element in the group has different inverse. The notation of the inverse is A inverse. Third condition, the operation is associative. For all A, B, and C in G, A star of B star C equal to A star B star C. The associative property of multiplication states that the way in which the elements are grouped in a multiplication problem does not affect or change the product of those elements. In other words, the product of 3 or more remain the same irrespective of the way they are grouped. The order in which the operation does not matter. G4, group is closed. For all elements A, B in G, A star B is also in G. If we have two elements in the group A and B, it must be case that A star B is also in the group. The non-empty set G together with the binary operation star is called a group if satisfying the above properties from G1 to G4. Example, addition and singleton 0. If we add 0 to anything in the group, we hope to get 0 plus 0 equal to 0. So we have found the identity. Now we need to find the inverse. Well, again, we have only one element. So what is the inverse of 0? We want 0 plus 0 inverse equal to 0. Well, 0 inverse plus 0 is also 0. So 0 inverse is 0. So 0 is in group. 0 inverse is also in the group. Associative, A plus of B plus C equal to B plus C plus A. Well, there is only one element A, B, C equal to 0. So 0 plus of 0 plus 0 equal to 0 plus 0 plus 0. If we take any element A and any element B, will A plus B in the group? Yes, since there is only one element 0, so then A equal to 0 and B equal to 0. Is 0 plus 0 in the group? Yes, it is. So it is closed. So 0 is the group with respect to addition. The integer z under the group operation plus form a group. The set of invertible n by n matrices M under the operation star, that is matrix multiplication, form a group. The z integer under the operation star do not form a group because 1 belongs to z is identity element. Any element other than 1 and -1 does not have an inverse. N is not a group under usual addition. Since there is no element E in N such that x plus E equal to x. Elementary properties of a group. Uniqueness of identity. Let G be a group, the identity element of G is unique. Let E and E dash be the two identity element of G, then E dash equal to E dash. Since E is an identity, also E dash equal to E, hence E equal to E dash. Uniqueness of inverse. For any A in G, the inverse of A is unique. Proof. Let B and C be the two inverses of A, hence AB equal to BA equal to E and AC equal to CA equal to E. Therefore, B equal to BE, which is equal to B of AC, which is equal to BA of C, which is equal to EC, which is equal to C. Group applications. Making the Rubik's Cube form a group. We can make the set of moves of Rubik's Cube into a group. We will define it by G comma star. The element of G will be all possible moves of the cube. The group operation will be defined like this. If M1 and M2 are two moves, then M1 star M2 is a move where you do M1 and then do M2. G is certainly closed-end star. Since M1 and M2 are moves, M1 star M2 is also a move as well as. Let E be the empty move, that is a move which do not change the configuration of the Rubik's Cube at all. Then M star E means first do M, then do nothing. Certainly same as just doing M. So M star equal to M. So G comma star has an identity. If M is a move, we can reverse the step of the move to get a move M0. Then the move M star M0 means first do M, then reverse all the steps of M. This is the same as doing nothing. So M star M0 equal to E. So M0 is the inverse of M. Therefore, every element in G has the inverse. To show the associative, we need to show that M1 star M2 star M3 equal to M1 star of M2 star M3. That is, we want to show that M1 star M2 star M3 of C equal to M1 star of M2 star M3 of C for any cube C. We know from above calculation that M1 star M2 of M3 of C equal to M3 of M1 star M2 of C, which is nothing but M3 of M2 of M1 of C. On the other hand, M1 star M2 of M3 C equal to M2 star M3 of M1 of C equal to M3 of M2 of M1 of C. So M1 star M2 star of M3 equal to M1 star of M2 star M3. So star is an associative. Therefore, G comma star indeed a group. Next example, musical notes form a group. The numbering of musical notes as follows. C, C slash D, D slash E, F, F slash G, G slash A slash B is numbered as 0 to 12. Now, Z12 is nothing but the musical notes of the above. Closureness. E comma F belongs to Z12, hence E star F is equal to A belongs to Z12. Associative. E comma F and F slash belongs to Z12, hence E star F slash equal to E star F star A, which is equal to A star F, which is equal to E star B, which is equal to D slash, which is equal to D slash. Identity. F belongs to Z12. There exists C belongs to Z12. Hence, F star C equal to C star F is equal to F. Inverse. F belongs to Z12. There exists G belongs to Z12. Hence, F star G equal to G star F is equal to C belongs to Z12. Therefore, the musical notes satisfy all the group axiom. Therefore, the musical notes form groups. Thank you all.